Let us now discuss about the ideal and non-ideal solutions. First of all, what are ideal solutions? And non-ideal solutions. See, ideal solutions are those which obey Raoult's law at all concentrations and temperatures. Okay. And if suppose Raoult's law is not obeyed, then they are said to be non-ideal solutions. Okay. Let us see the first and very important difference between the ideal and non-ideal solutions. It is basically the molecular interaction. See, when say two liquids A and B are mixed, A and B are mixed. In this case, if the interaction between the molecules of A and B is the same as what it was earlier between the molecules of A and those of B. That means if there are no new attractions, then they are said to be forming an ideal solution. If it is not the same, I mean, if the interactions between the molecules of A and B is not equal to the interactions what were there between the molecules of A when it was taken alone and the molecules of B when it was taken alone. Now, when I say the interactions between the molecules of A and B are not equal to that of the interactions between the molecules of A and the molecules of B. This not equal to refers to two different things. They may be either less than the interactions between the molecules of A or the molecules of B, or it may be, say, greater I mean, after mixing, interactions may be less or more. Interactions between the molecules of A and B are greater than those between the molecules of A or those between the molecules of B. I mean, what we have seen earlier. So, if this is the case, we call it a non-ideal solution showing positive deviation from Raoult's law. Okay. And if the interactions between the molecules of A and B are greater, then we call it negative deviation. So, within a non-ideal, we have two types: positive deviation, negative deviation. The interesting part is, if the interactions are less than what it was earlier, we call it positive deviation. And if the interactions are more, then we call it negative deviation. Let me give you some examples for positive and negative deviation. And let me show you what happens when two different liquids are mixed. After that, we'll see the different other properties. Okay. Let us consider an example for ideal solutions. The best example is benzene and toluene. See, both are aromatic hydrocarbons. See, when these two are mixed, there won't be any new attractions because both are of the same family. No new attractions develop between the molecules of these two. Okay. So this is said to be ideal. Now, for non-ideal solution showing positive deviation and negative deviation, also let us see some examples. Now, a very interesting example for positive deviation is ethanol and acetone. See, if you observe ethanol, you will have hydrogen bonds between the ethanol molecules, right? This is in case of pure ethanol, what you have. But when acetone is added, see, it actually disturbs the hydrogen bonds. And it, in fact, weakens the attractions between the molecules of ethyl alcohol. Okay. Because of acetone, now the interactions have decreased. So this is an example for positive deviation. Now let me also give you one more example. Acetone and carbon disulfide. In this case, the dipolar interactions between these two between acetone and carbon disulfide are weaker than, let me say, earlier interactions between the molecules of either acetone or carbon disulfide. Anyway, interactions have decreased. In this case, we say positive deviation. Remember, generally we get confused with this. Positive deviation, but the interactions are less. Negative deviation, where the interactions are more. I'll say why we are calling them as positive and negative in the next properties, but for now, remember the interactions, if at all, are less than what they were earlier, positive, more than what they were earlier, it's negative. Now, let me also give two examples for negative deviation. Let us consider uh, this example, phenol and aniline. See, when these two are mixed, look at the fact of how the interactions increase. So this is how new attractions develop between the lone pair on nitrogen in aniline and the proton of phenol. I'm calling it proton because anyway this will become partially positive and this one partial negative, right? As the bonded pair lies more closer to the nucleus of oxygen. So the new attraction is between the phenolic proton and the lone pair on nitrogen of aniline. Interactions have increased. Next, let us take this example. Chloroform and acetone. See, when these two are added, new attractions develop this way. So this is acetone molecule, and this is our chloroform. Between these two, new attractions develop. I mean, hydrogen bonds are formed between the oxygen of acetone and hydrogen of chloroform. So the interactions have now become stronger. So this is how we can say positive and negative deviations. In the first case, there were no new attractions, neither increased nor decreased. So ideal. If decreased, positive. If increased, negative. Okay. Yes. There are many such examples, and all the examples are very important. You need to remember them. Now, coming to the other interesting properties, let us take the vapor pressure into consideration. See, in case of ideal solutions, it can be given as the total vapor pressure is equal to the sum of the partial vapor pressures of the two liquids, A and B. It is because A and B are behaving as if they are alone even after mixing. No new attractions developed. Whereas, coming to the positive deviation, positive deviation is weakening the attractions. When attractions decrease, I mean, when the interaction between the molecules decreases, they can easily come up to the surface by overcoming the weak intermolecular attraction. They just not only come up to the surface but also escape into space. That means evaporation becomes easy when the attractions are less, isn't it? Lesser the intermolecular attractions. Let me write that. Vapor pressure is inversely proportional to intermolecular attractions, isn't it? In case of positive deviation, where you got lesser intermolecular attractions, or when the intermolecular attractions have become weak, no doubt the vapor pressure increases. The overall vapor pressure will be more. P total will be greater than the sum of the partial vapor pressures. Look at this. From now on, we are going to get everything greater, positive, more in case of positive, except the attractions, where for positive it is less, for negative it is more. You need to concentrate on this. Now, in this case, because the attractions have increased, I mean, because the intermolecular attractions have increased, evaporation becomes difficult. As a result, it will be this. P total will be less when compared to the sum of the partial vapor pressures. right? This is about the vapor pressure part. Coming to boiling point, very interesting. See, in this case, there won't be much effect on the boiling point. But in case of positive and negative deviations, see, in case of positive deviation, because P total is more, the boiling point, see, because vapor pressure and boiling point are inversely related. We can say, because the vapor pressure is increased, boiling point decreases. So boiling point will be less than expected. Whereas in this case, the boiling point will be more than expected. Okay. Now, the same thing is technically given as, see, because the boiling point is less than what is expected, we call these mixtures as a minimum boiling azeotrophs. These are said to be the maximum boiling azeotrophs. What does that indicate? Minimum boiling, maximum boiling. See, when I say minimum boiling, the boiling point of the mixture will be less than either of the components. Okay. Let us suppose the boiling point of A is 100 and the boiling point of B is 70 degrees centigrade. Now, in this case, it will be less than 70. The mixture will have a boiling point of less than 70. The azeotropic mixture will have a boiling point of less than 70 in case of positive deviation, more than 100 in case of negative deviation. Less than either of the two components is positive, more than either of the two components is negative. Let me give the same in detail. See, in this case, the boiling point of the mixture will be less than either of the two components. In this case, it will be more. Now, let me get into more details of what is azeotropic mixture. See, azeotropic mixtures are also known as constant boiling mixtures. As the name itself suggests, mixture will have one particular boiling point. That is what I said. In case of positive deviation, the mixture will have a boiling point less than either of the two components, only one particular. Two different liquids with two different boiling points. But when they are mixed in a particular composition, remember particular composition, every single mixture proper or a particular composition behaves as an azeotropic mixture. That means at that particular composition, the mixture will have a single boiling point just like a pure liquid. That is the reason why we call them constant boiling mixtures. Let me give you one example. See, if you consider a mixture of ethanol and water, when their composition is about 95% by volume of ethanol, 95 is ethanol, 5 is water. We normally call this rectified spirit. See, when the composition is this, it behaves as an azeotropic mixture. This mixture will have a single boiling point. Distills over in the same composition at one particular temperature. Two different liquids, but they just distill at one particular temperature. This is a speciality. So they cannot be separated from one another. So this is interesting. Let us take one more example. Of course, this is for negative deviation. Let us consider a mixture of nitric acid and water. Say this mixture, when taken with 68% nitric acid and 32% water by mass, I mean they are weight percentages. Even this also behaves as azeotrope. And boiling point of this azeotrope, of course, is 393.5 kelvins. The mixture having two different liquids distills over at one particular temperature. So that is a speciality of azeotropic mixtures, are constant boiling mixtures. Okay. So this is very interesting. Either they'll have a boiling point less than either of the two components or greater than either of the two components. Now let us take the other factors. See, if suppose 100 ml of A and say 20 ml of B are mixed, and if the total total volume is exactly 120 ml, you can call it ideal. No change in volume on addition, right? Now, if the same thing has a volume greater than 120 ml, then we call it a solution showing positive deviation. In this case, it will be less than 120 ml. Okay. Why? Why is it so then? It is because we know that in positive deviation, attractions are reduced. See, when attractions decrease, they just go farther. They just go away from each other. As a result, volume increases. Whereas in negative deviation, if you observe, the attractions increase. Interactions become stronger. As a result, they come closer. So, we observe decrease in volume. That is very interesting. Then, coming to heat change on mixing. Say in this case, no new attractions. So neither absorbed nor liberated in case of ideal. In this case, delta H mixing can be given as positive. That means this process is endothermic. Yes, of course. Because here, some bonds are broken. Bond breaking is endothermic. In this case, bonds are formed, interactions increase. Bond formation is exothermic. So, everything is related to the interaction part. Next. Coming to delta S mixing and delta G mixing, they are always the same. Always positive in case of delta S, and when it comes to delta G, it is always negative. You may be actually knowing this fact that there is a relation Gibbs Helmholtz equation, which can be given as delta G is equal to delta H minus T delta S, right? In general, for a reaction to be spontaneous, delta G must be negative, isn't it? Of course, there are several other factors, but finally, we decide whether a particular reaction is spontaneous or not on the basis of delta G. Delta G is negative, the reaction is spontaneous, right? Okay.